about linear transformation. Today I will discuss inner product of vector space. We all of us know the well-known vector R2 and R3. If we think the vectors of R2 as arrows, then consider two vectors. This is V1 and this is V2. Then obviously we have angles. Consider these angles as alpha. So we can measure length. Okay, consider this length and exist also distance. And this distance is denoted as dV2, V1, which is actually the length of V2 minus V1, which is this distance. Okay, this is the, we all of us know this is the V2 minus V1, which is denoted as D. Sorry, here not V2, here would be V1. This actual idea of inner product, norm and metric space of a vector space. Actually, inner product means angle of two vectors, length, and norm means length of this vector, and metric space means distance of this length. This is the actual idea of three space. Actually, at first I will say what is the inner product, then I will say norm and metric space. In inner product, consider two vector u and v, and in the operation inner product, it replaces two scalar, inner product u and v, which is actually dot product of these two vectors. Actual definition is, since inner product is dot product of two vectors, and we all of us know dot product is such type. Consider R3. Now consider two vector x and y. Now define the dot product is such type x dot y equal to, we all of us know this is actually x1 y1 plus x2 y2 plus x3 y3. Actually inner product is generalization of dot product. So if we consider RK, then we refer to this dot product as a inner product, and which is actually denoted as, inner product is defined as inner product x comma y, which is equal to x1 y1 plus x2 y2 up to xk yk, and this expression actually nothing but y transpose x. Are you getting? Well, that means actual property of inner product. Inner product on a vector space which captures the properties of dot product, which is used to define the notion of length and angles. So actual definition of inner product is, let V be a vector space over the field A. An inner product on the vector space V is an operation which takes two value. Here two value means vectors. V and W belongs to this vector space as an input and gives a scalar. Inner product VW belongs to F as an output. That means inner product always be a function, because here the input be two vector and output be one scalar. Inner product be a function from V cross V to F, where V be any vector space and F be any field. And this function satisfies following properties. Condition 1, linearity in first variable. If v1, v2, w belongs to the vector space V, then inner product v1 plus v2 comma w equal to inner product v1 plus comma w plus v2 inner product v2 comma w, and for C belongs to F and vw belongs to vector space, inner product cv comma w equal to C times inner product vw. Then our next property is conjugate symmetry. If v and w be two vectors in the vector space V, then inner product vw equal to always conjugate of wv. And if we consider the field equal to real number, then inner product wv conjugate always equal to inner product wv. Next property is positivity. If v is a non-zero vector, then inner product v with itself is a positive real number. That means inner product v with itself is a positive number. And when inner product v with itself is 0, even only if v equal to 0. Now let's see some examples of inner product. First example, consider v equal to Rn. Then the inner product is such type. Consider two vector x and y from Rn. Then inner product xy, which is actually the usual inner product, defined as summation I equal to 1 to n xi yi. That means x1 y1 plus x2 y2 so on. And you can see easily this satisfies all properties of inner product. Just try to oneself at first. Our next examples, consider the vector space V equal to complex number Cn and F equal to C. Here the inner product is defined as summation I equal to 1 to n ui vi bar, where u equal to u1 u2 up to en and v equal to v1 v2 up to vn. Let's verify, is it inner product? I will prove this. This is very easy type. At first, prove the linearity. First property is linearity. For this, inner product u plus v comma w, which is actually equal to summation I equal to 1 to n ui vi times wi, where wi equal to w1 comma w2 up to wn. Therefore, we can write this expression as I equal to 1 to n ui wi bar plus I equal to 1 to n vi wi bar. Okay, and this is actually our defined inner product. This is actually inner product uw plus inner product vw. Therefore, the condition of linearity has satisfied here. Next condition of linearity is inner product alpha u comma w, which is equal to summation I equal to 1 to n alpha ui times wi bar, which we can write as omit alpha I equal to 1 to n ui wi bar. Okay, and obviously alpha times this means our defined inner product u comma w. Okay, that means the condition of linearity has satisfied here. Now I will see our second property. Second property is conjugate symmetric property, which is such type inner product uv, we all of us know this is equal to summation I equal to 1 to n ui vi bar. Okay, and which we can write as easily I equal to 1 to n vi ui bar to the power whole bar. Okay, this is actually equal to summation I equal to 1 to n ui vi bar That means this is similar to inner product VU. Are you getting? Therefore, the condition of symmetry has satisfied here. Our next property is positivity. This is inner product with itself. That means U with itself. This is equal to summation I equal to 1 to n ui times ui bar. This is actually similar to summation I equal to 1 to n ui whole square. That means this is equal to u1 square plus u2 square up to un square. And this value obviously always greater than equal to 0. And when this inner product equal to 0, that imply u1 square plus u2 square up to un square equal to 0. And that imply ui equal to 0 for all I. And conversely, when ui equal to 0 for all I, that imply inner product 0 with 0 obviously equal to 0. Are you getting? That means since all condition has satisfied, so this is obviously inner product in Cn. Are you getting? OL. Similarly, if we consider V equal to all Fn, this is actually the Euclidean inner product. And similar to before, this is actually defined as this type. This is actually dot product. Are you getting? What is the Euclidean inner product? I will highly recommend you for higher study. These examples are more important. So, please pay attention in this topic. And if you have any queries about this part, about this example also, please do comments in comments. There exists some difference between inner product and dot product. Inner product actually the generalization of dot product. Dot product I have seen in physics for R2, R3 to find the scalars. But inner product and inner product can be scalar, vectors, matrix, integral, so on, different type of vectors. When we working on Rn, then we call this is the dot product, who is denoted as inner product of these two vectors is actually U transpose V. Actually dot product always be inner product, but inner product is actually more general concept. I will define different type of inner product. Here the vector space is set of all m cross n real matrices, and here the inner product is defined on these matrices such that since inner product is dot product, so inner product between two matrices is defined as trace of B transpose A, because trace means sum of diagonals, which is equal to summation I equal to 1 to m times summation j equal to 1 to m aij bij, where a equal to aij, where a is m cross n matrix, and b equal to bij, where b is m cross n matrix. Here this inner product actually same as the vector dot product. This is same as Euclidean dot product x transpose y. Okay, and this will satisfy all properties of inner product. Let's verify first property. First property is linearity property. Then this would be the three matrix A, B and C. Then A plus B comma C inner product equal to, by the defined mapping, this is equal to trace of C transpose A plus B, and this is equal to, by the property of trace, this is equal to trace of C transpose A plus C transpose B. And since this is trace, so this is equal to trace of C transpose A plus trace of C transpose B. Okay, and trace of C transpose A means inner product A comma C plus inner product B comma C. Are you getting? Therefore, first property of linearity has satisfied here. Second property, inner product alpha A comma B. And by defined function, this is equal to trace of B transpose alpha A. Which is actually summation I j alpha aij times bij. Now omit alpha from this summation, then this would be alpha summation I summation j aij bij, and this is actually equal to alpha times trace of the defined function. This is equal to trace of B transpose A. So this is alpha times inner product AB. That means condition of linearity has satisfied here. Property is conjugate symmetry. Inner product AB, which is equal to, by the defined mapping, this is equal to trace of B transpose A. Now, if we apply again transpose B transpose A transpose, this is equal to obviously trace of A transpose B, because we all of us know AB transpose is equal to B transpose A transpose. We all of us know B transpose to the power transpose always would be B, and since this is equal to trace of A transpose B, that means this is equal to inner product BA. Therefore, inner product AB is equal to inner product BA. Therefore, symmetric property has satisfied here. Next property is positivity property. Inner product A with itself. This is actually equal to trace of A transpose A, which is by defined function. This is summation I summation j aij whole square, and this is obviously always greater than equal to 0. And when inner product A with itself is equal to 0, that implies summation I summation j aij whole square equal to 0. For that implies summation I summation j aij equal to 0 for all I and for all j. Are you getting? And since aij equal to 0 for all I and for all j, this implies A equal to 0 matrix. Conversely, when A equal to 0 matrix, then inner product 0 comma 0 always equal to 0. Next example of inner product, we all of us know about the Fourier transformation. Here, I will create inner product as a function. Consider the function f and consider another function g. Then inner product f comma g is actually equal to integration a to b fx times gx dx. Okay, and here I have considered the function as a real valued function. If we consider the function as a complex valued function, then I will apply here bar. But now I will check for real valued function. I will check this will satisfy all condition of inner product. The vector is such type. Consider the point x1, x2, x3, and at this point the value of the function f1, f2, f3, also for g the value of the function g1, g2, g3, so on, gn, here fn. Now consider this discrete point as a vector. That means the vector here such type f equal to f1, f2 up to fn and g equal to g1, g2, gn. This is the idea to define construct inner product of two functions. Actually, this inner product would be an inner product on functional vector spaces. Let CAB denote the set of all continuous functions on the closed interval AB. Then for two functions f and g in CAB, we define the following inner product such as inner product f comma g equal to integration a to b ft gt dt. Okay. Now I will verify the property of all condition of inner product. To prove linearity, consider three functions f, g and h. Then inner product f plus h comma g equal to integration a to b ft plus ht times gt dt. And from this expression we can write is easily integration a to b ft gt dt plus integration a to b ht gt dt. And this expression is as defined as inner product fg, and from this expression this is we can tell as inner product h comma c. Therefore, the condition of first linearity has satisfied here. Our next condition of linearity for inner product CF, inner product CF with g, this is equal to integration a to b cft gt. Therefore, we can write it as easily, we can pull out this c by the integral, then this would be c times ft gt dt. And this is actually inner product f comma g. Therefore, the condition of two linearity has satisfied here. Condition I will see the symmetry. The second condition, inner product f with g equal to integration a to b ft gt, and we can write this as integration a to b gt ft dt, which is actually inner product g with f. Therefore, the condition of symmetry has satisfied here. Our next condition, inner product f with itself. This is actually integration a to b ft whole square dt, and this value obviously, since this is non-zero number, this is always greater than equal to 0. And when inner product f with itself is equal to 0, that implies f is equal to 0. Are you getting? Well, therefore, all condition of inner product has satisfied here. So this is obviously example of an inner product. Okay? Well, let's say one example. Compute the inner product 1 plus t square comma 4t. This is actually equal to integration 0 to 1 plus t square 4t dt. And if we find the integral, then this value would be 3. Therefore, the value of the inner product would be 3. Notice, this is the scalar number. Are you getting how we have to find inner product space? Well, today I will stop here. In my next video, I will discuss this topic also elaborately. But I will highly recommend you place the today's video with pay attention, because inner product space is very important for any competitive exam, not only competitive exam, for higher study, metric space, nonlinear space, functional analysis. This is more important. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel and share your friends also. Thank you so much.